Okay, it should be picking me up. It looks like it's picking me up. I think I fixed the K-maps 1 and 2, and there's still some other things I have to fix on this. There are plenty of places where uh, the older versions of Xilinx, and when I entered this stuff, it did not require the parentheses. Now it does. And so I've gone in and I've tried to do that and put in a bunch of parentheses to answer those questions. There are still going to be some like these that I haven't gotten around to yet. So what'll happen is you'll decide, I'll put in parentheses where I know they need to be. That's what I would do. And then you'll get it marked wrong because I will not have gotten to it yet. But I'll be going around and in all the free time that I have, I'll go around and be trying to fix all those so that it um, so that they're right. So then, if I were you, I would just try to put them in properly. So all your expressions, they should be in sum of product form. That means A and not B and C, all that within parentheses, and then or. Okay, so everything from now on for the rest of the semester that you turn in or that you do, you'll enter your stuff with standard VHDL. So I would say something like not A and B and C, or C and D, or and so on and so forth. Okay, so everything. Yeah, everything between ors is in parentheses. The not goes before the variable. Okay, the not goes before the variable to try to have some kind of um, consistency here. I would have A's, then B's, then C, then D, or A, and if there's no B and C, then the D. It would be just, I mean, it wouldn't be any problem to say D and C there, right? But I'm not going to enter it D and C. I'm going to say C and D. So no matter what we do, there's going to be trouble, right? No matter what we do, we're going to have some problems in this. Because as we go through this next set of slides, you'll see these using K-maps. And I mean, there's certain ways to do it where we'll probably get the same thing. But chances are our terms won't be the same or in the same order. Okay? Right there, I can't possibly put in every possible order. So right there, you're going to put it in an order that seems right to you by the way you were working it out. I'm going to put it in an order like this. Like here, you might have said down here, you might have, for some reason, said C and D, or then started with a not A and B and C. Still both the same, right? Nothing wrong with them. But Moodle looks at it as text only, so it'll mark it as incorrect. And there's just not, I can't. I mean, every time I find one of those, I could put it in this way too and give that as another possible option. But as soon as I do all that, they'll change the way I have to do it again. So I'm not doing it. I'll just look at it and say, yes, that's right or wrong. If you haven't started logic waveforms, it's an interesting uh, thing. I'll do this on the test to you also on the midterm, which should be coming up. When's the midterm? I haven't said yet, have I? Uh, We got T0, T0, T1, T1. You're going to look at this circuit and try to determine if A is low during this time, and B is low during this time, and C is low during this time. What's T0 going to be? Okay. And then you're going to come over here and put in 1 or 0. 1 or 0, 1 or 0. You like that? That's this to me. This is fun, but you guys might have fun in a different way than I do. So anyway, there's only 6 of them. That's a fun homework. Okay, let's see. And then we are going to until I mean I'm trying to fix them. That's all there is to it. I just haven't got there yet. As you'll see in, come on, this thing is slow as hell. You should have seen the mess I had with K-maps. I first started off with fixing distance ed students quizzes, and then I thought, oh, you know, will make sense. I'll fix them, and then I'll just copy them over day students. And I did that, and it kept both copies. And some of them, it changed from a group of 15 that was a group of 15. It now made it, because of the other ones that copied in, a group of 30. But then if I had another group of 15 and then it made it 30, it combined them. And now all of a sudden I had a group of 60. And you would not believe how long it's taken to try to fix that. As you see, it'll get there. This is the way these will work. Some of these, I hope, see here all of a sudden out of the blue, enter the minimum SOP expression for the variable y. Well, where the hell is the variable y? I don't see it. Do you? I just see, well, the first kind of stuff I used to use, the first online system we used, allowed me to say this one is the first question. This one, for some reason, I've tried and tried and tried to tell it, make that the first question, put it in a group by itself and say, just make that first. Still won't do it. So this is the why I'm talking about. So you come down here, and we'll be doing this in class, but if these are our 4 variables, this is what we get for W. There's a truth table for W. Here's a truth table for X. Here's a truth table for Y. To complicate it just a little bit further, this version of Moodle interprets a star as a wild card, so it won't show up. So we've got to change to use X's for don't cares. So you'll put in a star. I won't even be able to see it. It'll think it's taken a wild card. I'll see a space, so I'll assume that you put in a star. The ones that are out there that you may run into that are really, really stupid. Well, huh? Huh?
Why are they always, yeah?
But,
like music appreciation.
I don't know. Anyway, a long time ago, I tried to figure out how can, here's my Carnot map. I give you an expression like this or some other expression and tell you, give me the Carnot map. How are you going to give me the Carnot map? You can't draw it in Moodle. So I chose a way to do it that wasn't the very best way, confused the crap out of everybody, and this is the reason we've changed the reason we've changed to the way we're doing it now. There's a real simple way of doing it, and that's entering the summation form. Okay, but I wasn't thinking of that a long time ago. So I would take let's see, where is this? I would take something like this one, let's say this one right here, and say, okay, what you got to give me is the ones and zeros across here. So you were supposed to type in one space, where'd it go? Let me, one space, zero space, one space, one, next row, zero space, one space, one space, zero space, zero, zero, one, zero, one, zero, one, one. And gave my directions the way I thought, and people would go, what the hell are you talking about? Enter the string of ones and zeros. Some of you already saw it. So instead, I said, just give me the summation expression, which is how I tried to fix them all up now. So this would be, assume that this is already there, and all I want is a list of numbers. This is cell 0. 0, comma, there's 1 and 2, 2, comma, 3, 4, 5, 6, 7, 8, 9, 10. Did I put a comma in there? Yeah. Let's see. Then we got 11, 12, 13. I'm sorry, not 11. That's 10, 11. We got 12, 13, 14, and 15. So that's the way you're going to be entering them now. You're going to be giving me the cell numbers, okay? And that's called the summation form. And now that's a standard way of doing it. That's why I've changed to that. So you'll see that on these where that's what you've got to do. So here it says indicate below the summation expression for this Carnot map. So for this one it would be 1, 4, 6, 7. And that tells me I know now exactly where the ones and zeros are. Okay. Enough of that kind of stuff. I know you guys are just loving it. And we want to get done with all this stuff so that we can get started on the projects. And the projects are just tons of fun. I think they're fun anyway. I don't know what you guys will think about them. Okay, we're here. We're going to finish that today. I hope get into this. This one, we're going to probably skip the PLD stuff because I just don't see where we really need it. We do need to know how we have to enter the data to put on a chip, but do we really need to know why it has to be written in sum of product or product of sums? And it's because of the architecture of the chip, but yeah, we could go into a lot of explanation. I just don't think we need to do it. And so it shouldn't take too long to get into all this stuff. And I'm hoping we have a midterm before our fall break. And our fall break is right in here in October. So it's October 4th, 5th. It's the 6th and 7th. So we have a class on Tuesdays and Thursday, right? So it looks like it's going to be Thursday the 2nd that I'd like to have the fall or the midterm exam. All right. Now, let's pick up from here and keep going. Okay, so we're going to take this expression with and reduce it using a K-map. The first expression, A, B, C, D, or A, not B, and D, would put ones in these two cells. Anytime somebody doesn't understand why, I'd rather have you ask me now than have you asking me after the exam, right? This is a better day to ask. Anyone, I haven't had anybody come to my office this semester yet. So either I've got some real crappy hours that you guys can't get to, and I mean, I really shot for that. I looked at your schedules and tried to find a time when you guys were in class so that you wouldn't be able to come to my office. Uh, there, I did a good job, didn't I? There are two on my office door. There's two blocks there that say it's reserved for meetings. Okay, we don't always have a meeting during that time, but our department chair didn't schedule one class during that time, at least in our department. So that means those green spots are I'm either going to be in a meeting or I'm going to probably be in my office. Of course, I might be at lunch too, but even if my door's closed, knock and see if I'm in there. Okay? Because I think some of you need to come by if you're not understanding any of this. Okay, the next one. We have B and not C, and because we only have two variables, I think that's going to take up four cells, and that would be those. The B domain is the two center columns, and not C domain is the first two rows. So there, those are. The next expression, four variables, that means we pinned it down to one cell. A, not B, C, and D is right there, or and not D is right there. And then we finally put this one in. There's two ones there, but this one was redundant. Okay, now what we're supposed to do, and most of you remember this, we're supposed to find the biggest groups we can. We don't have to have redundancy. In some cases, if it says reduce it to the minimum, you don't want any redundancy. So our best two groups would be this, right? We got two groups of four. I could put in another group of four right here, but that would be redundant. And we're going to get into some redundancy in a minute. I can't have a group of six, right? And I can't group these four any other way. So the only other grouping I could have had was right here. And that being redundant, we don't really need it. Okay, and that gives me a B, not C, or A and not B. Okay? Okay, so don't care states. We are going to get, for right now, we'll leave it alone, but we will be getting into a bunch of don't care states. So when we get into those don't cares like we have here, see, I have this bad habit of not putting the zeros in there, and I probably should, but there's also these don't care states. When we have a don't care state, it's really true. We don't care. It can be a 0 or a 1. It's not going to have any impact on the way our circuit's going to operate. So when we have a don't care, you use them to make it easier for you or make the expression better for you. So if I'm saying find me the minimum, these four are always a good four to choose. Let's see, these four would work. These four are a possibility. Now we're making, as soon as we say this one is a 1 and I'm including it in my grouping, even though it says don't care, from that point on, we're going to consider it to be a 1. And that'll come up as the semester gets further along. It'll come up again and again and again. And it becomes really important that if you've included it in a group, it's become a 1 now. We could have these four. We could have these four. I don't think we'd need those four, though. So there's plenty of options here. I don't see one group of 8. Do any of you? Nope. I see these groups. I always like to do the outside corners because nobody ever thinks to look for those. And but that doesn't mean I had to do them, right? I could have done this here, but I still would have probably for this one and this one, I would have included out here because it makes that a smaller grouping or a larger grouping for these two ones. Okay, there's other possibilities. Okay, I'm trying to think where some other ones are. Okay, so some of these don't care states help us form groups and some of them don't. Now, it would be much better to have this group of 4 right here than to have this group of 2 and this group of 2. It would be much better to have that one big group of 4. So remember that kind of stuff. It's better to have this group of 4, I'm sorry, than this group of 2, and then this one by itself. So use these don't care states to help you. In this case, that one didn't help at all, so don't include it. Okay, so here's another possible combination I've got, and I'm asking why might this not be the best combination? I'm sorry?
A lot of redundancy.
Well, there is a lot of redundancy, and that, again, that depends on what you're wanting. If you want some redundancy, and we're going to see real shortly why you might want some, then that would be okay. The main one I see here is this grouping right here. I've got this group of 2 where I could have had a group of 4, and that would make it a little bit simpler to do that. So in doing this, there are more groups, more terms, more complex. They have more overlap, so there is more redundancy. In this case, I'm looking at that as a possible negative. And then the one group I pointed out has only 2 ones where it could have been in a group of 4. Now here's where redundancy is going to help. There's a possibility of glitches in your circuit, and we don't want them, right? You don't want anything to all of a sudden have a peak of 1 and then it goes away, or where it drops to 0 and then goes back to where it's supposed to be. Those are they call them hazards, and we want to. There are glitches and hazards. We want to plan our circuit so that they don't happen if we can. They can be. I have done some troubleshooting before where they were the problem. A glitch was the problem, but you can't find it. It's hard to find it. Now, how many of you have used one of the logic analyzers before? We had some great logic analyzers up there. They are gone now because nobody used them. Huh? Yellow probes? Yeah. Well, a logic analyzer, they were in that room 321, which no longer is a lab for us to mess around in. The logic analyzer is like could be up to 32 channel oscilloscope.
Don't they have them in that lab?
Huh?
Don't they have them in that lab that we got digital lab in? They're gone. Are they just moving?
They took them to surplus because nobody used them. Now, there was a good reason nobody used them, okay? But, now, they're very complicated to use. But an oscilloscope, the vertical axis measures voltage level. We're going to have on a digital circuit either high or low, period, right? That's all we're supposed to have. So we don't really need to have all this different functions for voltage levels. We just need high and low. The horizontal axis is time for a regular oscilloscope. For a logic analyzer, they're also time, but it's not an ongoing time. It is time in little chunks. It's like every 10 nanoseconds, or let's say 10, yeah, maybe nanoseconds. Every 10 nanoseconds, it'll go out there and sample all 32 lines. It might take it a few seconds to do that. And then it'll put out there it was a logic 1 or a logic 0. And then it goes back and it samples all those lines. And it puts out there it was a logic 1 or a logic 0. So it can't keep up with it in real time. So what can happen? Well, somewhere in there can be a little glitch, and we'll never know it. Plus, the glitch could be right when it catches it, and it could say, well, it was 0, but it would put that for that whole time period. It would say it was 0. That wouldn't be right either. So that's not why they're not good. They're great machines, but they were very, very complicated. Well, yes, sir.
So you turn it on and they would run and they would output something similar to the transient analysis box. But it would just read and store all the data in the buffer and then go back and read the buffer and output.
Now, the reason the ones we had were not that great, they were good. They were logic analyzers. They were complicated machines. There was a time, it's been a while, since I was applying for jobs, that I went and I was looking through their shop and I saw a logic analyzer sitting up on the shelf and it was dusty. And I asked the guy, I said, why do you have that up on the shelf dusty? That's probably, is it not functioning or what? He said, do you know what it is? I said, yeah, it's a logic analyzer. Why isn't it down here being used? And he said, you're hired. Boom. You know what it is? You know how to use one? I said, yeah. And he was like, he had bought it and nobody in his company has used it. And it helped troubleshoot so much. Now, what we had on ours at the time, we were working with the 68,000 and the 6811 microprocessors. Okay? And for both of those, for the analyzers we also had what they call a personality module. So in other words, this little module understood 68,000 code or 6811 code. So now what we could do, now this was cool, could run our programs and it wouldn't print out your program, but it would print out in order what instructions were being executed. So you're sitting there thinking it's going through boom, 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 like lines 1 through 10, and then going back up to 1 through 10, and then finally it gets down to 5, and it meets a condition, so it skips to 11. And if you're looking on the logic analyzer, it might never do that. How else would you ever find out? I mean, it'd be so hard to find out. This logic analyzer would be right there to tell you. So you could look at your instructions and see how they're being executed, or you could go out and look at the address bus or the data bus or the control bus and see what lines were going high and low. Absolutely fantastic machines for digital troubleshooting. But you need the personality modules for the processor you're working with. Otherwise, all you've got is all the lines, and then you've got to do a lot more of that in your head. I mean, I can look at the address lines for a while and the data lines for a while, And after a little while, I can start picking up what they should be and do some troubleshooting. But the length of time it takes for me to be fully aware of what data I should see when addresses, and what I should be seeing when, uh, it wasn't worth it. It took too much time to work with them, so nobody used them. I brought them up because of glitches. Uh, we could set them up also to run and run and run and run, because sometimes we would run until we hit a certain instruction. Sometimes we would run until we saw certain data on the data bus. Sometimes we would have it run and keep running until it saw a glitch, because we weren't finding anything anywhere else. So let's see if there's a glitch. And we'd see, stop on a glitch, and it would stop, and it would put a bunch of stuff in the buffer. It's always storing stuff in the buffer, but it would have it beforehand, see the glitch, and so then it would keep what it had beforehand and save a bunch more after that, and then display that on the screen for you to work with back and forth and try to figure out what was going on. Great machines, but we don't have them anymore. There's a lot of different reasons we can have these hazards. One of them up there says it's caused by differential propagation delays. That's a possibility. Minimal realization of a circuit might not be hazard-free. What do I mean by that? A minimal realization of a circuit might not be hazard-free. What I'm talking about there is we might have gone to the simplest SOP form, but it might not be written to be glitch-free. So we've got to fix that. Static hazards can be eliminated by introducing that redundancy into the group. So here's an example. We've got this circuit. We've got, let's say that F is equal to A and C, and here it's or B, C not. I should have written it at that time. I didn't write this all out in the standard VHDL. So there's our circuit. So if the initial inputs for A is 1, B is 1, C is 1, so we have a 1 and a 1, that's a 1. That 1 output causes a 1 here. Even though this is a 1, it's going to take a little while to go through here and produce, so at first this will be a 0, and then it will flip over to a 1. And wait a minute. If we had a 1 and a 1, I'm sorry, it would take it a little while to flip over to a 0, but having the 0 here doesn't really matter. This is still a 1. So the new set of inputs, let's say it's A is 1, B is 1, C is 0. So we've got, there's 2 different times here. This is, so don't let it confuse you. Yeah, it'll mess you up. But we got A is 1, that's fine. A is 1 here. C, it says, was a 0. It was 1 before. It went from a 1 to a 0. So the output here went from a 1 to a 0. Okay? So the output here, we got to wait on that. Now this C was a 1, so that was a 0. But now this is a 0, so this is going to a 1. Everybody following that? That's, okay, so now these 2 1s are going to produce a 1 here. So this output is going from a 0 to a 1, meaning our output for a moment there had a 0, and then it went to a 1, and it was because of the propagation delay in this inverter. Not much of propagation delay, but it's there, and it can cause a glitch. Well, how can we get rid of that? Here's one. You may not be able to find this in Xilinx. Sometimes you can if you really zoom in on some of those images for timing. You can see that, ooh, this might be a glitch because I'm down here measuring in picoseconds, and so this might be a glitch, but not always. So one of the ways you can handle this is what they're trying to show. See, I got this out of some other book. That's what I'm saying there, that they are trying to do this. If this is the original circuit, AC or B and not C, and we got A and C or B and not C, here they included this, which is, what's that term? A and B. So no, it's not the least, it's not the, uh, it's not the, why, I'm sorry, it's a simple word. I just lost it. It's not the simplest. Simple word. It took me that to get it. Simplest solution, but it could be hazard free. It'll keep that from happening. So what we end up doing is we get a circuit that looks like this, but now when this when we have this C going from 0 to 1, this one's taking care of keeping it a 1 here, and it solves our problem. And that extra gate, this extra part of the circuit, is called a hazard cover. It's called a cover. We put a cover on that one so that you couldn't see it. Instead of a Band-Aid, it's a cover. Okay, so now, how can we design state machines? I might ask you to design a state machine that won't have any glitches or hazards in there, okay? And one of the options for that is, now we'll find out, I see we haven't even gotten to the state machines yet, but when we get to the state machines, we're going to find out we can choose whatever we want for our state to be. It might be the first state, but we could call it state 4. The second one, we could call it, it is the second state, but we can choose a digital number to make it work in our circuit. And is that annoying you? I can't really even hear it.
I understand it.
You want me to go hit them?
I actually understand it.
Understand what?
The language.
Which language?
Song.
There's language over there. There's language in here too. Do you understand it?
Yeah, both.
Really? Is that messing you up?
Yeah.
2 languages at once? One language at once messes me up. Okay, let's go back to this. So we're going to try to do our best in designing a circuit that will be glitch free. And I know at this time we haven't even worked with any kind of state machines yet, but we will. And the best way to stop a glitch when you're designing a circuit is choose your states. And when you choose the next state, we can choose any one we want for a starting point, so I'll choose that one. But now if I want to go to the next state, I can't go to this, or this, because that's a diagonal move. But we can go to one of these 4. So we can, well, actually, we can go here if we want. But now we've got a possibility. Okay, what is this if we're looking at zeros and ones? We got 0, 0, 1, 0, 1, 1, right? So we got a 1 for A and a 1 for B, and then a 0, 0, 0, 1. So we got 1, 1, 0, 1 is this. This one is 0, 1, 0, 0. So what happened? More than one bit changed in making that move. And when you have more than one bit change in making a move, uh, you have the possibility of creating a glitch. So to prevent the glitches, you try to go horizontal or vertical in moving from one cell to another in your count. And what that does is it ensures that you're only changing one variable at a time. One at a time. So we could go to any one of those. So let's say we go to that one. That's, you just choose one. But I know when I chose that cell that I'm in for S, if I were to give it the binary number, let's see, that's, is it 12? No, it's 13, isn't it? 13 and then 14 at the bottom and 15 right below it. So do I say it's 12? Well, I was wrong. No, I'm just saying that cell 0 is adjacent to cell 2 and 12. Okay, so this one is cell 13 in binary. That should be what, 1101? Is that what that is?
Yeah.
Pierre says it is. It is. Okay, he's the man when it comes to this kind of conversion, right? Well, he is now, so if he makes a mistake, it's all his fault. We went from 1101 to the next one, which was 5, right? 0101. So we went from 1101 to 0101. Only one bit changed value. The first one, right? Now, if we go down one from there, we went to 7. Okay, and we were at 4. If we go from, or no, we weren't at 4. We're at 5. 0101. That's 5. To go to 7, that's 0111. We only changed one bit. To go over once is only changing one bit. To come down again is changing one bit. To go from the lower left over to here, those are adjacent cells. We only change one bit. In fact, that's one way that you can verify that they're adjacent cells. So I could move that whole column here. If I wanted to, I could move it over here, and this is adjacent to that, this one's adjacent to that, this one's adjacent to that one, and this one's adjacent to that one. Okay, so moving like this, that's only one cell. Oh, I'm sorry, it's one cell change, so one bit change. Going from here up to here is a one bit change, but I could have gone from here to here. This one was just to throw more stuff in there, but I could have gone from here to here and then here to here, and that's the same number of moves. Okay, well, what happens if it's one too many moves, but it makes the best glitch-free circuit? Well, go ahead and put that one in there, but you'll never hit that state anyway. But go ahead and put it in there for your design, and it'll help. Okay, so these states are not in order. It'd be better to have them in order. So in binary, I'm showing them like this so you could look and see that going from one state to another, only one bit changes. And it should, if we wanted them in the summation form, we'd have to it would make more sense to have them in ascending order. Okay? Okay, so having that only one bit change from one state to the next, it eliminates at least one way of eliminating a chance of having a glitch. There are going to be some times where you just can't do that. And you'll have to find other ways, and some of them might be putting a cover on there of some kind. Okay. I don't know if any of you have seen these before. The only one I know that Psalm and here is you. You've seen it though, right? And that's about it. That's all right. That's variable entered K-maps. Have any of you done that? Okay. Now we know we could go up to a 5 variable K-map. We can get 4 by 4. That gives us 4 variables. If we have a 5th variable, we have to stack 4 by 4s. Okay? And then we got to start thinking in 3 dimension. Kind of looks like Spock's whatever it is. His game. What is it? Huh?
It was some kind of chess game.
Chess game. I lose words. I lost that word for a moment. It's extremely aggravating to me to be sitting there going, wanting to get the word out, and I can't get it out. I'm sorry, but it happens. You guys just laugh. Say, that idiot can't even think of the word chess. Okay. Let's first start with looking at a 1 or a 0 in a K-map. Here we've got a 0, right? There's 0 in that one cell. In this other cell, there's a 1. It would be not A and B and C. Okay? We could say, I'm trying to, we wouldn't do this, but we could say that the 1 is not A and B and C and 1. It's still going to be 1. The other one we could say is not A. It should be not A. I don't know how that got so far off, but it should be not A, B, and C, and 0, and it would still be 0. Okay. What we end up doing is I could say here I can put the E and F in there or the D, and all I'm really saying is the same thing here. Instead of A or not A, B, and C, and 1, if I had that other variable out there, I could say and D. And then if D was a 0, that cell would be a 0. If D was a 1, that cell would be a 1. Okay? It's a little different. So that first group would be A, not A, B, C, and D. And this other group, they are both completely identical. One's E and F. The other one is also E and F. It's not E or F. So they are both identical. If they're not identical, you can't circle them. So that one would be saying I'm ANDing this group, which is A and not B, and I'm ANDing that with EF. Okay, now here's what was that? Don't let it get there. It'll clear up the more you work with it. So here are the rules. Variables may be entered into a K-map and grouped with ones or don't cares by following these rules. A variable can be grouped with a 1 anytime. We're going to work on a number of examples here. The ones that are grouped with a variable must form a redundant group without the variable. See, I might not be able to get the words out, but I know what's going on here. And a variable may be grouped with don't cares without any kind of restriction. So let's see what that means. Now we'll go through some examples. Here's 3 not D's and 2 D's and a 1 in that map. Now, the D and not D are not the same, so they cannot be combined. But one of the rules there was a variable can be grouped with a 1. So I can say I have a group at the top that is that whole row. And I can have the 2 D's grouped together. Now, it also says, though, and this is where most people mess up on this, the ones that are grouped with a variable must also form a redundant group without the variable. And so that means that 1, unfortunately, there's no other ones there to group it with. So we have to make one group of that 1, 1. So here's what we would have. Okay. Now, how would that be written out? Well, that top row normally, without looking at, if we're just acting as if they were 1s, we would say that that was not C. But since we've got that not D in there, we'd have to say it's not C and not D. Below that, if those 2 D's were a 1, that group would be called not A and C. But with the D's in there, we're going to say that's not A and C and D. And then we have that lonely 1 all there by itself, and that happens to be A and B and not C. So here we go. There is a great place to stop and ask a question if you can think of one. That question might be, can you go through that again?
That's a pretty good question.
That is a good question, isn't it?
Can you go through it again?
Oh, sure. Does everybody have this? Let's go through it again. We can say that as long as 2 groups, as long as a group is identical, like that E and F there, I can group them together. And now I look at that group as being, instead of EF, as just saying those are 1s, okay? And I write it out the way I normally would, and that would be A and not B. But there's an EF in there. So I would have to say it's ANDed with that EF. On this other one, it's a lonely D out there. If it were a 1, we would be saying it is A naught, B, and C. But then there's a D in there instead of a 1, so we have to AND that D to that group.
What is the point of the variables?
Huh? Why would we do this?
Yes.
Because how many circuits would you have that are real circuits that are restricted to only 4 variables? You might have 20 variables, and you're trying to simplify something. So now you got to start entering, you don't want to work in multi-dimensional K-maps, so you got to start working in other forms. Actually, once you get up to like 6 or 7 variables, you don't even want to use K-maps anymore. You want to do something completely different. So there's the rules again. Variables can be grouped with a 1. That 1 that's used in that group, or the ones that are used in that group, must be in a redundant group without the variable. There could be 3 1s and 1 variable. So we include all the, those 1s have to be grouped without that 1 variable there. Now it's real nice if the variable's grouped with the don't care. You can just group with that and not worry about anything else out there. So we got this, and that not D looks like It can be grouped with the other not D's, right? So these two can be grouped together. This one and this one can be grouped together. But according to those rules, a variable can be formed, or a variable can be grouped with the one. So I can take this whole group here. And so that would be this. If these were just ones, I would call this group C naught. Is that all right? You got it? And then I would have to AND it with that not D there. So we have a not C and not D. But there's that one. It has to be redundant. I don't have anything else to AND it with here. See, I'm lucky. I can't hear anything.
I don't know if that's luck.
See, and if I really didn't want to hear it, I have a little switch on these to turn them off and on. And my wife does ask, do you have them on? And if I say yes, she'll say, let me check. No, I'm kidding. That does not happen. It doesn't happen. I never listen to her. So she knows I'm not listening. So these two D's are not ANDed with any one, so they're by themselves. If these were ones, we would say that this group is B and C, right? Oops. No. We would say it's, that's not right. What is that? Not A and C. You guys almost let me get away with that. Pierre was just about to say something. He was catching me on it. And then this one's all by itself. That one we do have to have a value for because it's grouped with these D naughts. So here we've got an A, B, and C naught. So here's our groups. Here's our resulting expression. Okay, now let's verify it. Because I know that you guys are all out there and going, this is a bunch of hokum, right? You think it's hokum? I don't know, ask Sheldon. Our Sheldon would say hokum. I'm sorry. You don't know what I'm talking about.
No, who's Sheldon here? I know who Sheldon is, but I don't know the Sheldon here.
They, who was it? Kuthar and Howard were trying to set him up with a dating service. And so they were trying to use words like Sheldon would say. And Sheldon was like, no, that's a bunch of hokum. And Howard said, see, or no, Kuthar said, see, we put on there hokum because we knew our Sheldon would say hokum, not BS. Okay. And then they matched him up with Amy and started asking themselves, what have we done? It's really sad that I know that.
Dude, I love it. I don't know why. It's awesome.
Anyway, we want to verify. Let's see if this really works. What I'm going to do is take that same expression, okay, and we're going to put it in. Isn't this the one I just had? Not A and C and D, and then no, it's not. This is a different expression.
No, that's right.
Is it the same as that?
Yeah.
Okay, so let's start with it. The first thing we have to do, we don't have to, but what I did was expand it out a bit. And honestly, now that I'm looking at it again, I have no idea why I expanded it. I don't have to.
You're on a lot of sugar.
Huh?
lot of sugar in
Could have been. So I expanded it, and that first term then would need a B in there. So I ANDed that with B and not B, and then you see the CD there too. And so we get A naught, B, C, D, and A naught should be not A, not B, and C, D. Now, I'm skipping the middle one for right now, and I'm ANDing the last term with D or D naught so that I could bring it into it. And I come up with that, and then I take the C naught, D naught, and expand that out, and I end up with a bunch of hokum.
Hokum, yes.
Because there was no reason to do this. Now I simplify and get rid of ones that are well, here I'm saying put it in the right order. See that A, C naught, D naught, B naught? It should be A, B, C, D there. And so fix those so that those are right. And I got the arrows, I think, in the wrong place. Right? The arrows should be here and here and here.
I think you're just maybe
The last four.
So anyway, I end up with this, and then I replace all my, and oh, this is a lot of fun. What? I must have had not a thing to do. And then I replace all my inverted variables with zeros. This is to get a number. This is so I can change it to summation form. That's all I'm doing. That's what I've set up here. I'm converting to summation. I could put it in the map and it would tell me what the summation form is. But we've got put zeros for for ones with bars over it, ones there, and we end up with this. Okay, now that's a 7, that's a 3, that's that 13, there's a 12, there's a 4, a 0, another 12, and an 8. So I can get rid of one of these 12s because I got 2 of them, right? And then I put them in ascending order, and I get 0, 3, 4, 7, 8, 12, 13. There are many other ways of doing this. I don't know what I was thinking that night. But now that I've got those, I can just put the ones in those particular cells. Now remember, I'm trying to verify. I'm going to go back a whole bunch and come back to 83. I'm trying to verify that this expression that I had here is the same. Here I put it in with variables in a 3-variable K-map. I entered the D's and the D naughts. And here I put it in a 4-variable map and got that. Now let's simplify. And when I do, I get this group, that group, that group. Do you see any other groups or any other ways that I could have grouped them? And so we're left with not A and C and D, not C and not D, and then A, B, and not C. And that is the same as the one on 66. Okay, so let's at least finish this up today. We'll be able to do it. Here are some other ones. Here's a lot of fun. We can circle, we can use the stars or not use them. That's up to you. So I would use this group and have B, because that's what that would be if this was a 1. And then I AND that with this R and not S. And because it's don't cares, I don't have to do anything else with it. Here is interesting. This is not the same as that, so I can't keep these together. I can group these two together, and I can group these four together. And then I get this without the variable would be C. And then I AND it with the T. And then this one without the variables would be not A and not C. And then I AND it with those two, the R and S not. Here's one that's lots of fun. That looks like a mess, doesn't it? You guys soon are going to start asking, where do I get my stash? Okay, look at this. I've got two variables in there, and now they're ORed instead of ANDed. So I come up with these two groups. And I could say without the, and I've got this group down here, but here I could say this is these four, which is just B, and AND it with this. And then multiply through the B, and I get B and R, or B and not S. And it, or I can just start from the beginning and group that R with the stars and group the S with the stars and just write it out that way. Doesn't matter. And then here I've got A or C, because the one in the star, I would rather have that grouped with the star so it simplifies a little bit. I can also show it like this, right? And because I'm multiplying through by the B, it's okay. Here's some really messy stuff. It can get worse. We got not R and not T, or R and T, and it's real close. There's a T here. But what can we do? This is about all we can do. This C and not A and the T. This is all by itself. It's not A, not B, not C. And then we can AND it with this R naught and T naught, and we can AND it with the R and the T. Kind of messy, but that's the best we get on this one. Well, this one looks like fun too, doesn't it? We can combine these. We can combine these two because they're identical, and I can AND those four together. So I did that and got A naught and C and the T. Here they're identical, so that would be like these two cells, which would be A naught and C naught and R and not S. And then this one is B and whatever this one is, R not S. Now you might be saying, how is this going to help us? Well, you're going to be having a state machine who's got 4 flip-flops for memory, and they're going to be A, B, C, and D. And then you're going to have input switches. Let's say there's 5 of them, R, S, T, U, V. And all of them have some impact on your circuit. So you've got A, B, C, D, R, U, S, T, V all coming into play in your circuit. It can make a mess of things. You're going to what?
Just hand it off to somebody else and pay them to do it.
I'll do it. But I'll charge you for it. And here's one. Really, we got 2 minutes and 2 slides. Here's one. I can group all of these together if I wanted to. And I would end up with this one big group, which would be my X or not V. And then because you have to group that one with a redundant grouping that does not include the variables, I had to do this, and that turned out to be B. And that is that. And we will pick up on that on the next one next time with circuit simulation in Xilinx. And what I might have to do, since this looks a little different, I might have to just go through and, yeah, this is a different version. I might have to instead go through this with the new version.
You have to do it, you have number 2.
Okay, I hope you guys had a great day, heard everything.
Hey, 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 they're